Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
Subject: Soil Mechanics. Chapter: Shear Strength of a Soil. Mohr Circle. So as we've seen in the last class that related to stress at a point, we have taken this example where the soil element is being subjected to the normal and the shear stresses at sigma x and sigma y as in this figure, and we have calculated the components of the stresses. We have taken this as q or tau yx, and this is tau xy, and we have taken the, consider this plane which is inclined at an angle theta. Okay, so when we speak about the Mohr circle, we take the two axes like this, and x and y, and on this axis we consider the 2 points of reference. So first point is the plane at which your sigma y is acting. So we consider here in this case as sigma y as greater than the sigma x. As in the previous cases, we have taken the same case. Sigma x and sigma y is greater, so it plots on the normal stress axis. This x-axis is normal stress axis, y-axis is your shear stress axis. So on this normal stress axis, it's been plotted here. It's a sigma y. Okay, so this is sigma y value. Somewhere it comes here, and on this on this plane, there is a clockwise shear stress equals to q. So shear stress, again, since it's a clockwise, so it's from sign convention it's a negative, so it plots here. So it's been plotted here, and on this axis the value is sigma x, so it falls here somewhere. So first point we've got it like this. This is the first point. And then the second point, sigma x comes here, and on this plane, on this plane, the shear stress acting is in anti-clockwise. So anti-clockwise in the plus direction, q value. So this is the second point under consideration. And so if you join these 2 points, we'll get to one line like this by joining this. So if you look it back very carefully, this distance is nothing but your q or tau yx, and this distance is also equals to q, and this is the center of circle you will get. And by plotting this center of circle, you can draw, you take this as the center and radius equals to this, you plot the circle like this. So this is called as the Mohr circle. And this is your sigma x. Do not confuse, this is your sigma x, and you'll get this as the minor principal stress, which is nothing but sigma 3, and you'll get this as this is your sigma y value, and this you will get it as sigma 1, which is nothing but your major principal stress as sigma 1. So generally it's been very clear from the diagram that sigma 1 equals to, this is radius of circle. From this point you should mark this radius of the circle. So this plus this is your sigma 1 from the circle. But this distance, you can calculate this distance. This distance is your sigma x distance. This is sigma x. This is sigma x. This is your sigma y. Okay, this is your sigma. So sigma and this is your q again. So so sigma y minus sigma x is this distance, and divided by 2 is again this distance. So this is equal to, let's suppose I take it as general a. So a is equal to sigma y minus sigma x upon 2. Very clear. And if you want to calculate the radius of the circle, and this radius, if you turn it back, it becomes your tau max again. So this is your tau max. So tau max is the radius of the circle. Tau max is the radius of the circle, which is nothing but the square root of, this is the hypotenuse distance, this is q, and this is your a distance. So this is nothing but sigma y minus sigma x divided by 2 whole square plus q square. This is your sigma, this is your tau max value, and also it is equal to the radius of the circle. And if you calculate from this diagram, this is your a distance. So sigma x plus a. So if you add sigma x value to the a, you will get the distance from the origin point O. So for this distance O, so this distance plus your radius of the circle, you will get sigma 1, and this distance minus radius of circle, you will get sigma 3. So I'll write a very general expression for the major and minor principal stress from the Mohr circle as follows. So I'll write the sigma 1 or sigma 3, not the divided by. So sigma 1 or sigma 3 is equals to this distance, which is nothing but sigma x plus a. So sigma x plus a is equal to sigma x plus sigma y divided by 2, because if you add sigma x on a, you will get sigma x y by 2 minus sigma x by 2 plus sigma x, will get plus sigma x by 2. So plus sigma y by 2 plus sigma x by 2 is sigma x plus sigma y by 2, and plus obviously your radius of the circle. So this is your plus, you need to add radius of circle, which is nothing but the square root of sigma y minus sigma x by 2 whole square plus q square, or the shear stress, applied shear stress square. So that's all about the sigma x and sigma 1 and the sigma 3. If you want to get sigma 3, yes, obviously for sigma 3 you must deduct the radius of circle from this expression. So that's how you will get sigma x and sigma y. And however, if you want to get the any normal stress and any value of the shear stress acting on any plane inclined at an theta, how to get? Now you see, this is the angle theta. So when your theta is 0, these are the stress conditions. So when theta is 0, but when theta is 0, this is the stress condition, though it is represented by this line. So when theta is 0, but as you go, but if your theta becomes 90 degree, the stress conditions are here. So this is represented by this line. So if you go 90 degree here, you need to go 180 degree over here. So obviously if you have to go anti-clockwise, then similarly you have to go anti-clockwise from this direction. So from anti-clockwise from this direction, you need to go anti-clockwise at an angle of 2 theta, obviously at an angle 2 theta, and then you will get the sigma and tau value respectively at that plane. So it's very simple. And also you can get the same way by locating pole. So what is pole? See, pole is nothing but a point from where you can just mark a theta in the Mohr circle, and you will get the respect to the normal stress and shear stress acting on that plane. So how to get that pole is a very important. You see here, this is a plane like this. So this is the plane here in the Mohr circle. So from the plane, this plane is horizontal. So you need to draw a horizontal line like this. So you have drawn the horizontal line from this point, because this is the stress condition over here, and this is the stress condition over here. So this you will get the point we call it generally it as a pole. So this point, how to get that point? You have drawn horizontal line from this point, and also from this point, this is a vertical plane, so you need to draw a vertical line like this. So you will get an intersection like this. So this is nothing but your pole, and from pole you can take theta anti-clockwise. That's all, and you will reach to again to the same point. You again reach to the same point, because again this as the pole. That's how the definition of pole comes. And again we'll see the simplified version of this when there is no shear stress acting on the soil mass. See, it is a very simpler case. So when there is no shear stress, it is only been acted by sigma x and sigma y. So rather than calling sigma x and sigma y, so as you know that sigma y is greater than the sigma x in this case, hence your sigma x becomes a minor principal stress sigma 3, and your sigma y becomes a major principal stress at sigma 1. So this is sigma 1 and this is sigma 2. So henceforth we use the same expressions. And if you want to draw a Mohr circle corresponding to this point, so it's quite easy, because you directly get the 2 points and the radius as follows. So this is your sigma. So this is your sigma 1 value, which is nothing but your major principal stress, and this is your sigma 3 value, which is your minor principal stress. And just you need to draw a Mohr circle by considering this as the diameter. So you will draw it like this way. This is your Mohr circle corresponding to this point. And it's very simple as in this case, because there is no shear stress acting on this and this plane. So these are itself becomes a major and minor principal plane depending on the magnitude of the normal stresses. So this is your sigma n, and this is your tau axis, and this is your radius axis. So now the point of the discussion come over here is, see, this is the Mohr circle corresponding to the one value of sigma 3 and sigma 1. So obviously if your sigma 3 goes on increasing, what will be the value of sigma 1? And this is whether in the terms of the total stress or whether this becomes in the terms of the effective stress, how will be the Mohr circle, and how will be the failure envelope, and how to determine that envelope. Again, that is the point under that is a concept that needs to be discussed over here. So we first of all consider that the Mohr circle, which is shown in this figure. So if this touches your failure envelope like this, so if this touches your failure envelope, then this becomes a point of tangents to it, and these are the conditions at failure. So this is minor principal stress at failure, and this is your major principal stress at the failure. And now, as you know, that the shear strength, because you must consider here that not always the shear stress acting on the failure plane is a maximum, because see, this is the failure plane, and at failure the conditions are here. So the tau is still lesser than the tau max, and also the sigma is lesser than the sigma 1 but greater than the sigma 3. So not always it's like that. On that failure plane the normal stress is maximum or the shear stress is maximum. You must remember here that on the failure plane there is a critical combination of the normal stress and shear stress, which leads to the failure of the material or a soil. So now, as you know that the shear strength is nothing but your C plus sigma tan phi. So this intercept at which your sigma is 0, so this is nothing but your C value. So I'll just extend this linear part to the back side. So this is your cohesion C, and the angle made by the failure plane with respect to the horizontal line over here is the angle of internal friction phi. And see, this is C, and if this is phi, then this becomes C cot phi, because tan phi is C divided by this, so this distance is equal to C divided by tan theta, so it becomes C cot phi. So, and obviously this is your sigma 3. From this point to this point it's sigma 3, and if you take this triangle into consideration, ABC, this is perpendicular, and from this origin point, if this is the failure plane, this is the orientation of failure plane with respect to this. So inside the soil mass, so if you draw this point, this is your theta value, and this theta is your failure plane, that what it makes with respect to the major principal plane. Remember, so theta is the inclination of a failure plane with major principal plane. It's not the horizontal, it's with respect to the major principal plane. So if this is the theta value, then obviously from the diagram this becomes a 2 theta, and if this is the pole, then you can again relocate the pole, because this is the sigma 1 and this is the horizontal line. So you must draw a horizontal line from this point, and this is sigma 3 and this is a vertical line. So from sigma 3 you draw a vertical line, so it intersects here, so this is becomes your pole and this becomes your theta. That's all. And from the geometry, this theta is equals to 2 theta. You can easily prove it. So this is theta. So when this becomes theta, this becomes theta, and from this diagram, this is your perpendicular 90 degree, and this angle becomes equal to the phi. So I consider this as suppose a y. So your y plus phi plus 90 degree is your 180 degree in triangle ABC. So therefore your y will be equal to 90 degree minus phi, and obviously this y plus your 2 theta is equal to again 180 degree. So you place the value of y equals to 90 minus phi in this expression. You will get 90 minus phi equals to, this is the 90 minus 5 plus your 2 theta equals to 180. So I'll write this 180 minus 2 theta. So therefore you will get this goes here, this goes here, so plus 2 theta minus pi equal to 90 degree. So you will rewrite as 2 theta equal to 90 plus pi, and therefore theta equals to 90 plus pi divided by 2. I'll write simply theta equals to 45 plus pi by 2. And in all cases, this is the standard expression. This is the standard expression for the theta value. Theta is the inclination made by a failure plane with respect to the major principal plane. So that theta is represented in terms of the angle of shearing resistance as 45 plus pi by 2. So that's the first part of the derivation. In the second part, we must correlate sigma 1 and sigma 3 with the C and phi values, because once you determine C and phi, you must able to draw this Mohr circle and the field, and you must say that whether it's a safe or unsafe, or if it's failed based on the sigma 1 values, obviously. So now from the triangle, if you look back this same triangle ABC, you will get the sin phi equals to, this sin phi value equals to BC upon hypotenuse. So BC is nothing but your radius of the circle, which is nothing but sigma 1 minus sigma 3 divided by 2, divided by your this value C cot phi plus, this is C cot phi plus your sigma 3 plus radius of circle. So plus sigma 3 plus radius of circle is sigma 1 minus sigma 3 divided by 2. So you will get sigma 1 plus sigma 3 divided by 2 plus C cot phi whole thing into sin phi equal to sigma 1 minus sigma 3 divided by 2. So if you multiply both sides by 2, you will get sigma 1 plus sigma 3 into sin phi plus 2C cot phi into sin phi equal to sigma 1 minus sigma 3. So if we take sigma 1 here and sigma 3 over here, you will get sigma 1 into 1 minus sin pi, sigma 1 into 1 minus sin pi, and sigma 3 over here after taking equals to your sigma 3 1 plus sin pi plus 2. C is caused by sine, so sin will get cancelled. You will get 2C cos pi. So you will get this total expression, and hence you will get sigma 1 equals to sigma 3 1 plus sin pi upon 1 minus sin pi plus 2C root of cos phi upon 1 minus sin phi is root of 1 plus sin phi upon 1 minus sin phi, and this is your total expression. So this is generally called as n phi value, 1 plus sin phi upon 1 minus sin phi. This is also equals to tan square 45 plus pi by 2. We'll check it later on. This expression sigma 1 equals to sigma 3 into tan square 45 plus pi by 2 plus 2c tan 45 plus pi by 2. You'll get this expression, or again you can rewrite this as sigma 1 equals to sigma 3 n5 plus 2c root n5. So this is the final expression. You can use any these two or this expression. You can use any of these expressions as a correlation between the major principal stress and the minor principal stress. But again, you must from the Mohr circle you can easily determine that this Mohr circle, if it just stretches to the failure envelope as given by the Mohr Coulomb. So this is the failure condition, and on field we test the soil sample in the lab, and we take this C and phi values, and from the field condition you can take this sigma 3 value and you can correlate that if the sigma 1 at field, if it is less or greater than the calculated value. So if it is obviously be the less, then you can calculate the margin of factor of safety that the soil will have. But again, this C and phi depends on the how well you test the soil in the laboratories, and what are the stress conditions, what is the pore water pressure conditions that you keep, and what do you mean by the all several conditions such as the drained and undrained condition, and how well you will keep the consolidation going on, and what will be the rate of the loading, which again determines the pore water pressure which will be generated in the lab, and as well as you must correlate those parameters in the field so that you have the better estimation in the field and better factor of safety in the field. So we'll stop by deriving these expressions and the Mohr cycle. I hope you understand it, and in the next class we'll proceed with this determination of shear strength parameters of the soils and phi. Thank you.